Now we need to look at the Bohr atom and quantified angular momentum, whatever that is, but we will find out. When you fire alpha particles at some thin gold foil, most of the particles went through, but some of them bounced back, and that went against everything that people knew about the atom at the time. What they understood was that most of the atom was like a positive kind of doughy stuff, and the electrons were small negative things. So these other particles, which were positive, would just cut through like a knife through butter. But what actually happened was this. Most of the particles did just fly through. Some were deflected slightly, but some of them basically bounced back. This shouldn't have happened. And it happens basically because all the charge and all the mass is concentrated in these small centers called nuclei. And this is where we got the nuclear atom from. So this alpha scattering experiment, it gave rise to the nuclear atom, an atom with a nucleus. So Rutherford made this interpretation. He saw it like a kind of mini solar system, and it's called the classical mechanical solution. So the nucleus with a concentrated mass of positive charge, that's what he concluded, that the electrons were basically in orbits, a bit like planets around the sun. The electrons were in orbits around the nucleus. They could go in any orbit and go anywhere. They can take any orbit. That was what Rutherford saw as being the solution. However, Niels Bohr, there were some problems with this, and I'll go on to explain what they were. He gave his own interpretation of what was inside the atom. And this is called the quantum mechanical solution. He uses the idea of quantum mechanics, the idea that electrons, which are particles, can behave like waves. So he looked at this wave particle solution to this. So he basically had his model, which had three assumptions. The first one, the electrons in an atom exist in stationary states. They're in one state and they basically stay there, unless they're made to go into another orbit, let's say. The electrons can move from one state to another by absorbing or emitting a packet or quantum of electromagnetic radiation, like a photon. So if it's in a low energy state, it can absorb a packet of energy and jump to a higher energy state. Then it can jump back down to a low energy state by emitting a packet of radiation. And the last one, which needs a bit of explanation, is that there's this property called the angular momentum of an electron. It's like the momentum, but because it's going around orbiting the nucleus, it's called the angular momentum. The angular momentum of this state is quantized, and it only has integral values of h divided by 2 pi, which basically means there are only certain states that exist. And we'll look at the first point, because electrons in an atom exist in stationary states. Why is that? This is the argument. The electron, as it's going around in an orbit, because it's accelerating, would lose some energy and it would spiral into the nucleus, releasing photons as it did so. But actually electrons remain in this orbit without emitting electromagnetic radiation. So they're accelerating, supposedly, but they're not emitting these waves, which means they're staying in a fixed orbit. So this is what he means, the stationary states that the atoms are in. We do know that they do emit photons, and that's basically what happens is when it goes from a high level, a high energy state, to a lower energy state, and that's the next assumption. Electrons may move from one state to another by absorbing or emitting a quantum of electromagnetic radiation. Here we have an atom with 1, 2, or 3 orbits, or 3 states. The electron absorbs a quantum of radiation and can move up to a state with a higher energy. Alternatively, when it moves down, it emits a quantum of radiation. And this is what's going on here. The electron here drops from level n is equal to 3 to n is equal to 2. And this change in energy, delta E, will emit a photon of frequency f according to delta E is equal to hf. The third point is the angular momentum of an electron. in a stationary state is quantized. It only has certain values, and that's going to be equal to n h divided by 2 pi, which means h over 2 pi, or 2h over 2 pi, or 3h over 2 pi, and so on. So let's look at this thing called the angular momentum. We see it's mv times by r, which is basically its momentum times by the radius that it's at that time. And it's only going to have certain values. H over 2 pi, 2h over 2 pi, and so on. So the angular momentum is mv, which is, you know, as being the momentum times by r. Now, you know that an electron, which is a particle, can also behave like a wave, which means it has a wavelength. And the idea is there are a whole number of de Broglie wavelengths that fit around the atom. And we'll look at this. And lambda is equal to h over mv. That's the de Broglie equation. So it's like a standing wave, let's say. This is a standing wave between two nodes here. Or we could have this as another standing wave. And we have different allowed states in a regular standing wave, with where the boundary conditions are that there are nodes at the edge, at the end of this string, or whatever it is. In an atom, you can basically bend this standing wave around the atom as long as it fits around the atom at that distance. Here we have 1, 2, 3 full wavelengths that fit around this atom. That's on n is equal to 3. This one is n is equal to 2. We have 1, 2 wavelengths fitting around the atom. This is just 1 wavelength. We also know that the distance around the atom is equal to 2 pi r, the circumference of a circle. But we know that this circumference is going to be an integer number of wavelengths. So we can say that m lambda, which is a certain number of wavelengths, will be equal to 2 pi r. Let's rearrange and make lambda the subject. So lambda is equal to 2 pi r divided by n. And this is equation 2. Now, you notice that if we equalize the second equation with the first equation, we can get rid of lambda. So h divided by mv is equal to 2 pi r divided by n. So if we rearrange to make mvr the subject, we find mvr is equal to h divided by 2 pi. And that's what we needed to find out. That the momentum, the angular momentum, is always going to be a number times n times by h divided by 2 pi. In other words, it's quantized. Only certain angular momentums are allowed. And here we have another simple example here. This is n is equal to 4, which is this level here. We have 4 complete wavelengths going around here. So that's basically how that works. Problems with this model? It works well with hydrogen atom, which is a very simple atom. You've got a single positive charge and you've got 1 electron. But it didn't work very well with multi-electron systems. So with, for example, with helium atom and so on. But it also did work with a singularly ionized helium, which is obviously 1 electron and nucleus. It didn't explain why some spectral lines were stronger or more frequent than the others. It should be more frequent. It also didn't account for the splitting of lines to produce double lines. Some lines which should have been single lines were actually very two close together lines. But that was explained later with a property called spin, but we do not need to go into that. So, this is a summary. Niels Bohr came up with a quantum mechanical explanation of the atom. Electrons in the atom exist in stationary states. The electrons can move from one state to another by absorbing or emitting radiation, and these states only have certain values of angular momentum, and that will be equal to n times pi, h divided by 2 pi.